start the class, and we start here. But before, I want to go back to make sure that you understand. Like last time I made a mistake in the equation, so I want to make sure that you have that equation right. For example, when you have a connecting wire, you can change the resistance by changing either the length. So as you increase the length, what's going to happen to the resistance? Increase, right? Makes sense because the charges have to go a longer way. So the resistance is going to increase. And I can also change the area, the cross section, okay, the thickness of your wire. So if you increase the area, what's going to happen to the resistance? It's going to decrease, right? Because it's going to make it easier for the flow of charges, right? So a resistance like a connecting wire or any load. Okay, so each time you have a resistance or a load, and I will show you like an example. So each time you have a resistance here, so it could be a connecting wire, it could be a load or a resistor. It will convert electrical energy into heat. Very good, right? So the amount of heat it's producing, okay? So the amount of energy produced per unit second, it's called the power, okay? So in the case of a resistance, it's going to be RI squared. So the square is here and not there. So what is I? That will be the current going through the resistance or through the load. And so the R is just going to be the resistance. You can also say, so it depends what is given to you, that energy, okay, produced per unit second, okay, so it's the rate of flow, the flow rate of heat. It's going to be also, you can also write V squared over R, and V is the voltage across the load, or the voltage across your wire, or the voltage across the resistor. Is that clear? Now, the other equation, P equals V times I, is always true. Okay, it doesn't matter if you are looking for the energy produced by a power supply or consumed by a load. It's always true. So if you want to decrease the heat, either you cannot change the current, okay, because maybe you have a heater and the heater needs that current. So the way you can do it is to increase the size of your wire. So that's why if you have like a washing machine or things like that, they consume a lot of energy. So you need to have very thick wire to decrease the resistance so you don't start a fire. So microwave as well. You see, when you look at a microwave, they have thick cables, okay? They are not thin. Now, if you cannot change R, so that will be the case for transmission lines, like in that case. So you don't want to change R because you don't want to have thick cable because that will cost too much money. Copper is expensive. So instead, what you do is to decrease the current, okay? But if you decrease the current, you increase the voltage. So that means that high tension here lines, you need to have a very high voltage, a small current. So the electric company, they are not going to lose too much money because they are losing to heat. Okay, so most of the energy will be transferred to your house. Is that clear? Okay, I wanted to make that clear because, okay, the other thing to connect with your chemistry, that effect here, it's called the joule effect. Okay, it's named after James Joule. So maybe you learn about him in your chemistry class. He's very famous because he understood that heat or thermal energy is a form of energy. Heat is just energy in transfer. So he did that very famous experiment. Here you have a weight. Okay, that's going to fall. The way it falls, so it has potential energy that you can compute, right? Are you with me? Remember from last semester, mgh, that will be the potential energy. That potential energy, okay, will be used to turn the wheel, and the wheel is turning. What's going to happen to the water? You have friction, so it's going to warm up. And he was able to find the equation for thermal energy. So he was able to show that thermal energy, okay, is a form of energy because you can convert mechanical energy, potential energy here to mechanical energy to heat. Okay, so that's why it's called the joule effect. Okay, so that was just a parenthesis. Let's go to demo. Quick demo. So for example, here you can make a resistance here just with a wire. Okay, you keep winding a wire and you have yourself a resistance. If I connect that to a 6-volt battery, it's gonna get very hot. Okay, I'm gonna burn my fingers because I want to show you how you can measure the resistance. Can you see here? So this is called a multimeter, and resistance here. You see the ohm. Okay, so that's where I want to go. I don't expect a lot of resistance here. I go to here and I don't know what they put in those chemicals inside those carpets, but I'm becoming very allergic. So anyway, so you see here, so I'm going to measure the resistance here between here and there, for example. And what do you read? Okay, ohms. Okay, so it's a very small resistance. Now I can make myself variable resistance by moving this. And for example, here you're going to have uh, 20 ohms, right? So I can change the ohms by sliding it here. So now you have how much? If it keep stop moving, about 4 ohms. Is that clear? So just having a wire, okay, you can have a resistance and you go around and you can change the resistance, right? Exactly what is funny. Is that something funny that, no? Oh, good. So then you can have what we call resistors. So these are very special components, okay, that have resistance and their job is to limit the amount of current, or they can also turn electrical energy into heat. So for example, if I measure here the resistance, you're going to get about 15, about 15. Okay, so that's one thing I wanted to show you. Okay, circuit in parallel. Okay, I want to show you that. Okay, so first I'm going to show you the simulation. And so this is what type of circuit do I have here? The screen. Okay, so what is it called? A circuit in series, right? So it means the load, they are following each other. So if you close the switch here, they are not very happy. They don't get the 30 volt that they want. And as you increase the number of loads, you're going to decrease the current because you increase the resistance. And you can measure the current here. How much do you get? 0.75 amps, right? And we have seen, in addition to that, okay, so what do you think? Take your calculator. What do you think using Ohm's law? What's going to be the voltage across here? So you do 20 times 0.75, right? What do you get? 15? Okay, thank you. Don't space out. I see people spacing out. Don't space out. 15 volts, yes? And then I'm going to measure here. What do you expect? Huh? Across this one, what do you expect? 7.5 exactly. Okay. So 15, 7.5. How much is it here? 7.5. So when you add them together, it's going to be 30 volt. But each one of them is not happy because it doesn't get the 30 volt that it wants. And plus it doesn't get the current that it wants. Okay? So what's the math? We can replace the three of them by a single one equals to one resistance. The equivalent resistance is equals to 40. Do you all agree? Okay, when you have resistance in series, everything happens like you have a single one, and the value will be just the sum. Okay, so let's see. What did we say we have to replace it with? 40. You just have to be patient. Okay, let's measure here. What's the current? 0.75 amps. Okay, so that's the trick to find the current produced by the power supply. So this is not good. Okay, we don't do that in a house. Instead, we use what it's called a circuit in parallel. So it means you have all the loads. You see, they are the same loads, but now each one of them is connected to the power supply. So it's like they are doing their own business. They don't mind the others. So everything happens, they are alone with the power supply. They don't know that you have other loads as well. So you see, you close the switch here, and each one of them, it's going to get what's going to be the voltage across each one. 30 exactly. Very good. Okay, it doesn't have to share nothing. It gets its 30. So this one is very happy. Okay, and this one is also very happy. And this one is also very happy. Okay, and the current now, what do you think the current is here? So what's the voltage? 30. Okay, the resistance is 20. So then you have 30 divided by 20. It's going to be 1.5. Okay, now it's much, much happier than before. And then, because before it was 0.75, now it's 1.5. That's what it wants. And this one is, so 30 divided by 10, 30 divided by 10 is 3. And here it's going to be 3. So the price to pay, there is always a price to pay. If you have 3 and 1.5, what do you expect? How much do you think you're going to drain from the power supply? So it's like water flowing, okay? So you're going to have 1.5 gallon here and 3 gallon and 3 gallons. So altogether, how much you need? 7.5. Very good. So 7.5 amps. So it's like if in your house, if you play the music and you turn on the microwave and you dry your hair, all those machine can work at the same time, but of course you are draining more current, so you are spending more money. I mean, you are draining more energy. Except that sometimes here you have a fuse because you don't want to go over 20 amps. So if you keep turning on loads all at the same time, at some point you're going to reach the maximum 15 amps or 20 amps. So of course you have a safety fuse that will break the circuit. Okay? This is how it works. Okay? So the main thing here is that all the loads get their 30 volt and I'm draining 7.5 amps. So that could be your hair dryer. Oh, this is a hair dryer, has a very large resistance hair dryer. Then you have, I don't know, your computer, and then you have whatever gizmo that you have, all working at the same time. So now is the time, get your calculator, the TI. I will show you how to find the equivalent resistance. So we need that's not my calculator. So get your calculator. Let's give you time. I think this is my, no, this is the calculator. Okay, so the goal is to find the equivalent resistance. So what's going to be the resistance? You can replace all of them by a single one, such as you can have 7.5 amps as a current. Do you understand? So I'm going to remove everything. I'm going to say how to find the equivalent resistance, such as I can say everything happens, okay, like all those loads merge into one with one resistance. You're not going to add them up. So you're going to do the following. So I'll show you step by step, and then I will show you the equation. And I just lost here. Okay, so you take, what was the first one here? Was 20, do you remember? So we have 20, 10, and 10. So you do the following. It's the recipe. You take 20, and then you take the reciprocal. So to the minus 1. Do you all have that function with your calculator? Okay. Otherwise, you do 1 over 20. It's the same thing. Plus, okay. And then you do 10, and you do also take the reciprocal. So plus 1 over 10. Okay. Plus, and you do that with all the loads. So here I just have 3. So 10 to the minus 1. Okay. And then you go enter, and you flip again. So you take the answer 0.5, and you take the reciprocal again, and you get 4. So I claim that everything happens like you have one single load, and the resistance is 4. So let's see if it works. Let's see. Does it work? 7.5. So that will be the magic recipe in order to find the equivalent resistance. You take all the load and you do what I did. You take the reciprocal, you add them together, and then you take the reciprocal. Okay? So I will show you another example. Except that I forgot to show you another demo. So let's go back to here. So remember last time we talked about internal resistance? So I'm going to measure the EMF. EMF meaning what's the voltage across the power supply when no load is connected. So you have that. I'm going to measure it here. And it says, do you see? Yeah, no, I'm going to push here the same. Yeah, it's about like 4.5, 4.5, 4.5, about 4.5, right? But because those batteries are getting old, inside them, okay, you have a sneaky internal resistance. And if I want to connect a load here, okay, I will, if it's new, okay, if there is, if I just bought them, then the internal resistance should be 0. But as they get older, the internal resistance increases. So it means that when I want to measure the voltage now and I have a load connected to it, what you read? I don't know if I can put my finger here and do that at the same time. It's about 4 volts, right? It's about 4 volts. So I have lost some voltage. Where did that voltage go? Across the internal resistance, right? So when you measure here, that's called the terminal voltage. I have lost about 0.4 volt. That 0.4 volt is across the internal resistance inside. Do you see how it works? Everything is clear? So you have 4.4 we begin with, or 4.3 minus the voltage across the internal resistance, and then minus the voltage across the load. So the load is not happy, okay? It doesn't get everything it was promised. Plus I have also resistance across the connecting wires. Okay, so let's go back to here. Okay, so let's try to solve this one. Okay, so I have three loads and they are all the same. They are all the same. I have a power supply of 1.5 volts, and I'm gonna find the current drained by the battery, and I will show you. So remember that you have a textbook, so make sure you go over the textbook as well. Oh, by the way, I wanted to tell you, if you are taking the MCAT, as we go along, you should get a prep book for the MCAT, huh? And then do the problems relevant to what we are doing. So we are doing electric circuit, so you should open your book for the MCAT and do the problem. Okay. Plus, if you have any question, I can help you after the class. If you do a problem from the MCAT and you don't know how to do it, I can help you if it's relevant to what we are doing. So let me show you the methodology here. So we start from the same thing here. You have 1.5 volt, but now you see when you have a circuit in parallel, it's like you have more waves, right? And so that's why you can have more current drain from the power supply. So here, let's go back to here. So what's going to happen? You're going to do it this way. I'm going to make parallel circuit. You have one load, okay, and then you go to the ground. And then you have another load, and then you go to the ground. And then you have another load, and then you go to the ground. Okay, so that way you keep in mind it's like water flowing, but now the water has three ways to go. Okay, three paths. Now you can use that schematic as well. That will be the one from your book, I think. I think that comes from your book. So you have electricity flowing here, and then some of it will go in that branch, some of it will go in this branch, and some of it will go in that branch. Is that clear? Okay. So the way I like to do it is this way. You're going to see why. Now, so this is 10 ohms here, 10 ohms, 10 ohms, and 10 ohms. So what do you think the voltage drop is across here? By how much it's going to fall? So it starts from here. What's the height here? 1.5. This is the ground. So all of them will fall by 1.5, right? They all have, if it's connected in parallel, they all will be provided by 1.5. That's what I show you with the simulation. So 1.5. Now, can you find for me the current? So I'm going to have the current I1, current I2, and the current I3. I don't know why I have 210 ohms. Okay, so you use Ohm's law, right? Okay, so you multiply, so 10 times the current equals the voltage across the resistance. So I1 it's going to be 0.15 amps. I2 it's going to be, the voltage drop is still 1.5, so it's going to be 0.15. So that's going to be I2. And I3 is going to be, of course, because they are the same resistance, right? So because they have the same resistance, they have the same appetite for energy. Energy is voltage times current, so they have the same voltage, so they need to have the same current going through them. So let me ask you something. Imagine water flowing here. How much current do you need to drain from the power supply? So if you have 0.15 and 0.15 and 0.15, so how much do you need to drain from the main supply, from the power supply? Very good, 0.45 amps. Okay, So it's very much, it works like water flowing. So you have three pipes. So like this, you have three pipes. So of course, here, if you have 2 gallon, 2 gallon, 2 gallon, that will be 6 gallons here flowing every second. So it's the rate flow. Okay? Are you with me? So let's see if my mathematical tool trick is working. So now I want to say, okay, I have my 1.5 volt and I want to replace all of all those loads here by one single resistance. I call that the equivalent resistance. Okay, and now I know that it's gonna drain 0.45 amps. Okay, so it means I want to put all those loads here in one black box. Okay, I don't know what's going on inside, but I know that the voltage drop will be 1.5, and I want to know what could be the load here, one single load, okay, that could replace all of them, such as I'm draining the same amount of current here, and the voltage drop is the same. So use Ohm's law again. Okay, so you're going to do 1.5 equals 0.45 times the equivalent resistance. So the equivalent resistance is, you do it, do it. Take your calculator, do it. Very good. 3.33333. Repeating. Ohm, right? So let's use our TI to check if that makes sense. So this is circuit in parallel, right? So let's take each load. So you have 10 to the minus 1, okay. And then you have plus 10 to the minus 1, okay. Plus 10 to the minus 1, okay. That's going to be 0.3, okay. And you take reverse, take the reciprocal, and you get 3.333. Do you see how it works? So what's the equation? The equation is 1 over the equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3 plus. So you find the reciprocal and then you flip. But usually when I say that, students get confused, so I rather show you the steps, how to do it with a TI. Are you with me? Right? So this is a circuit in parallel. So you see, the price to pay is that every load is happy as a student who get an A in physics 2054, but there is a price to pay. You are draining more current, right? So you are draining more energy. So this is the schematic. So this is the same as that one. Okay, it doesn't matter how you place your connecting wire, because you know the two of them will be connected to the power supply, so the two of them will get the same voltage drop. Okay, so this is why in a house you don't use circuit in series, you use circuit in parallel. So usually from the outlet you get 120 volt AC, okay, and all those loads here consuming energy have to be in parallel. And as you increase the number of loads, you're going to increase the current that you are draining until you reach the maximum. Then you could start a fire because of the resistance, you know, if the heating effect, so the fuse will open. In addition to that, let me ask you something. That's something I forgot to tell you here. If I don't know if I show you that. I can show you. I can show you. I can do the demo. So do you agree? It's a happy load here. Okay, you agree? So I'm gonna make a circuit in series, okay, with the three of them. Okay, so I'm gonna connect them. I have to make a closed circuit. If you don't see, let me know because I cannot look up and look here. See that? So this is a circuit in series. Uh, are they happy now? No, not so much, right? They get very dim because not only the current has been divided by 3 if they are the same resistance, plus the voltage also is divided by 3, so not so much happy. Plus, and that's the thing I forgot to tell you, if one is broken, okay, so I'm gonna unscrew this one. What's gonna happen to the other one? They all go out, right? I'm opening the circuit. So that's another issue. So that's why even for the Christmas, the Christmas lightning, we don't do it in series because if your cat, for example, eat this one, all of them will be dead. So instead, we use parallel. So this one is happy, okay? We're gonna make another one happy. So we're gonna connect, I can connect here if I want. Okay, so now it's in parallel, it's happy. And then I can add another one. I can add as many as I want, no problem. The only issue is that I'm going to drain more current from the power supply. Okay, can you see? Now I don't have to connect here, I can connect there because that will be the same voltage drop. So if I connect here, I can make it to stick here. It's going to be the same thing. Okay, so that's a circuit in the parallel. So all of them are happy. All of them will have the same voltage drop. Each one of them will drain the current it wants. Now, if one of them, if your cat comes and, chew on this one, it's fine for the other one. Okay, they will still be on. You see how it works? Okay, so let's go back to here. So in a house, all the loads, okay, will be in a parallel circuit. If one is not turned on, it's not going to affect the other one. Here, you're going to have a fuse because as you increase the number of loads, you're going to drain more current and you want to make sure that you don't go over 15 amps or 20 amps. With a battery, there is a maximum. Okay, so it's not a problem with a battery because you always have a maximum of 1 amp, for example. But with those, um, because that power supply goes to the power plant, then you can drain theoretically as much as you want. So that could be dangerous. Okay, any question? So it's very much like now you have the power supply, you have branches here, and they can each branch can drain as much current as it wants. Okay, so for example, do the computation with your TI without looking what they are doing. And can you find the equivalent resistance with your TI to make sure you know how to do it? Right, everyone has a TI. If you don't have one, I can raise your hand. You can borrow mine. So you have a 30 ohms, a 30 ohms, and a 30 ohms. So you take your TI, okay, you do 20, take the reciprocal, okay, plus 30, okay, so you do 30, you take the reciprocal, plus 30, you take the reciprocal, and then enter, and then you take the, exactly, again, and you get about 8157 ohms, okay, that's how it works, okay. Um, So let's do 3, 6, and 9. Just to make sure you know how to do it. So you see, this is a circuit in parallel. All of them will get 18 volt. Okay. And I'm going to find the equivalent resistance. So you go 3 to the minus 1 plus 6 to the minus 1 plus 9 to the minus 1. Enter. And to the minus 1, you get 1.63 ohms. Okay, so the thing to remember is that the equivalent resistance is always smaller than the smallest one. So typical conceptual question, when you have a circuit in parallel, okay, the equivalent resistance will be always smaller than the smaller one. If you have a circuit in series, it's the opposite. The equivalent resistance will be always larger than the smallest one. Okay, did that. Okay, let's try to do this one. What do they want? Okay, so what you can start with is by drawing, you know, the way I do it. And what do they want? Let's just answer the question. A, equivalent resistance 2, and the power. So what's interesting here is that even though it's AC, Ohm's law still apply. So when you have an audio system, you don't need to convert to DC. Okay, audio works with AC. Okay, so there is no, like in my laptop, I have to turn AC to DC, but not with the audio system. And you have speakers. Speakers always have small resistance because inside you have a coil, and for that to work, you need to have a large current. So first of all, I'm gonna draw it the way I like. So 6 volt, and then I have two branches. So one branch here, boom, 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 and one branch there, boom, boom, boom. And I have 4 ohms here, and I have 8 ohms here. I have I1, I'm gonna have I2. And let's see what we're gonna do. We're gonna they want you to find the equivalent resistance. So we're gonna say everything happens like you put that in a black box. Everything happens that your black box is equivalent to a resistance RQ here. And that will be the current drained by the power supply. Okay, so you take your calculator and we do the same. Okay, so you do 4 to the minus 1 plus 6 to the minus 1. Enter, that's going to be 2.4. No, I did a mistake, right? It's 4 and 8. That's going to be 2.7 ohms. Do you agree? Okay, so that will be actually how much current here you are draining from the power supply. Okay, so you have that much current drained from the power supply, and then a little bit will go to that load, and a little bit goes to this load. Okay, so let's find I1. So you just use Ohm's law. Yeah. So you have two resistance here, 4 and 8. So you do 4 to the minus 1. Okay, if you don't have reciprocal, you do 1 divided by 4. Okay, 1 divided by 4. Enter, plus 1 divided by 8, enter, and then you do 1 divided by what you get, 0.375. Okay? But it's easier if you have the reciprocal, of course it's easier, okay? You do 4 to the minus 1 plus 8 to the minus 1, enter, and then you go to the minus 1. Is that clear?
So did you need to put it's supposed to be
Amps. No, no. No, I'm confused.
on the left diagram, yeah.
No. So here it's a 2.7 ohms. Sorry. Thank you. 6 volt. Okay, so can you find the current I? 2.333. So it's going to be 6. So you do 6. 6 divided by 2.666666666, and you get 2.25. Do you get that? Right? I equals 2.25 amps. So I claim, but we're going to check, that the current that you drain here will be 2.25 amps. That's what I claim. Let's check. Find I1 and find I2. Find I1 and find I2 using Ohm's law.
Use the equivalent resistance and when to use the separate resistance.
No, so in that case, you didn't have to do that, right? You can find I1 and you find I2 and you add them up and you will get the same thing. But then when it gets more complex, so for example, you have parallel connected to a series connected to a parallel, so then you will have to find the equivalent resistance for everything. Okay, it's a good question. In that case, you don't even need to do that. You can find I1, you can find I2, and then you can find I. That's what we're going to do here.
So I is the total current that's supplied by the receiver.
That is supplied by the power supply. I here, it's the current supplied by the power supply. Okay, so it's like the water. Okay, the total water, and then you have I1 here, and then you're gonna have I2 here. And then it's combining together. Is that clear? Hmm?
The currents they add up.
Yes, they're gonna add up. They add up. I1 plus I2 equals I. So I1 is what? So the voltage drop is 6. So 6 divided by 4, and you get 1.5. Yes, 1.5. How much is I2? The power supply, 6 divided by 8. How much is that? Okay, 0.75 amps. Now, if you add them together, I1 plus I2, it's going to be 2.25 amps. Of course, you say, okay, what's the point to find the equivalent resistance? Why do we make it more complicated? It's because circuit can be more complex. You can have parallel connected to series and parallel again and so forth and so on. So in that case, you will have to find the equivalent resistance. So anyway, question 1, find the equivalent resistance. That's going to be 2.7 ohms. Question 2, find the current drain by the power supply. That's going to be 2.25. And I don't know what's the question. The power, okay, the power, okay, converted by each speaker. So a speaker is going to do two things. First of all, it has a resistance. So some of the energy, electrical energy, will be lost to heat, and some of the energy will be converted to sound. Okay, so a speaker turns energy into heat and sound. Of course, you touch your speaker at some point, it's going to get hot, right? So anyway, they want you to find the power consumed by that speaker here with a resistance of 4 ohms. So you can do V times I, or you can do RI square, or you can do V square over R. Okay, I'm gonna do V square over R. Okay, I can use that equation because that way I don't deal with decimals, but you don't have to. So the voltage drop is what? 6 square divided by 4. How much is that? Hmm?
I don't know.
9 what? What? 9 what? 9 what? So for the 8 ohms, that's going to be V square over R. So it's going to be 6 square over 8. And what you get? 4.5 watt. So what's the total energy consumed? Exactly. That's going to be 13.5 watts. Yes? Let's find the power supply, okay, by your power supply. So let's do V times I. What's the voltage across the power supply? 6. What's the current going through your power supply? 2.25. Very good. 2.25. And what you get? 13.5 watt. Okay, so whatever goes in comes out, right? So input equals output, conservation of energy. Now, what you have here is that the current is going through the power supply, and then it's split into I1 and then I2. So I equals I1 plus I2. So the best way to do it, imagine water flowing in a pipe, okay, and then it's splitting in 2 branches. So which one gets most current? The most current, is it the 4 ohm or the 8 ohm?
So the power supply.
The 4. Yes, of course, because that will be the energy provided. That energy provided will be consumed by this one and consumed by that one. So it means if you have 10 cookies, for example, available, maybe this one is going to eat 2 cookies and this one will get 8 cookies, for example. It's always, no, it's conservation of energy. So if you have, for example, 10 cookies, one will get 2 cookies, the other one will get 8, but 2 plus 8 has to be 10. Or you can, it's because the energy provided will have to be equals to the energy consumed. Is that clear? So which one will have the most current, the 4 ohms or the 8 ohms? 4 ohms, 1.5. This one has 0.75. How many 0.75 goes into 1.5? What's the ratio between them? Huh? 2. So why is that this one has twice the current? Because it has half the resistance. Okay, so Ohm's law V equals Ri. So the voltage drop is the same. So if you divide the resistance by 2, the current will be divided by 2. This one stays the same. So if this one goes down, this one has to go up. So twice the resistance, half the current. So each one gets whatever it wants according to its resistance here. Is that clear? About energy, so if you have a energy supply of 10 watts, okay, and so that will be the energy produced by the power supply every second. If you have load number 1 that has an appetite for 6 watts, so guess how much load number 2 gets? 4 watts. So it's according to its appetite. Every single load gets whatever it wants according to its resistance. But there is a conservation of energy. It has to add up to 10. Okay? Whatever comes in has to come out. Doesn't work for calories, okay? It's not true that calories in equals to calories out.
So like how do you explain like when you daisy chain like multiple would it be experience like I don't explain like if you daisy chain each individual system.
So this is in parallel. So you know it's in parallel when every single load gets the same voltage. So when it's in parallel, everything happens like it's alone. Okay, it doesn't care about the other ones. They are not interfering with each other. But if you are in series, if you have a series, what's gonna happen is that, let me show you here. If I put one load, no, that's not a load. So now it's happy because it's alone, right? So you have 3 amps. But now if you multiply the load by 3, okay, so now you have 3 of them. So like 2 of them. Now you see that the current has been divided by 2. Instead of having 3, I have 1.5. So it's not happy because alone it's supposed to have 3 amps. And now it gets only 1.5 because when you multiply the number of loads by 2, and if the loads are the same, you divide the current by 2. In addition to that, the voltage is also divided by 2. The voltage is divided by 2 because they have to share, so each one of them get 15. So not only they have half the current, they have half the voltage. So if you divide by 2, you divide by 2, you divide by 4. So they get 4 times less power. So they are not going to work properly.
That's a series.
That's a series. As you increase the number of loads, you're going to decrease the current. You decrease the voltage across each of them. So they don't get the energy they would like to get. So in parallel, each one is doing its own business. They are ignoring each other out and they get the current they want and they get the voltage they want. Except that the price to pay, of course, is that you are draining a lot of current here from the power supply. Is that clear? Okay, so what do you think this is here? Is it a circuit or a parallel? Parallel. Okay? Parallel. You see? Each one, if you follow one connection here, you go to the power supply. If you follow the other connection at the end, you go also to the power supply. Connecting wire does not matter. So if one is 150 watt and this one is 150 watt, 50 watt. So first of all, which one is the brightest? The 100 watt or the 50 watt? they are in parallel. So more watts means what? More energy. More energy means they will be brighter. Okay? So the 100 watt alone will be brighter than the 50 watt alone. Yes? Which one has a larger resistance? That's a typical conceptual question. It's the 50 watts, right? That's it was in the pop quiz, or it will be in the pop quiz. I forget. But anyway, now they are happy because it's in parallel. So if I close both switch, how many watts I get? 150 watt. So with that, you have the choice between 50 watt, 100 watt, or 150 watt. Okay? You have those three-way light bulb. So you can make it dimmer or brighter. Is that clear? So alone, which one is the brightest? 100 watt. Therefore, alone, which one has the largest resistance? 50, very good. Okay, so because it's limit more the current, so it limit more the energy provided. Is that clear? But if you put them in series, the one with the largest resistance, the 50 watt, will steal everything. Okay, so it will steal all the voltage. So it will be the brightest, which we don't want. So that's why we have circuits in parallel and not in series. Okay? Any question? Okay, so why don't you try to do one? Okay, so help each other. Staring doesn't help. So if you are taking the MCAT, you can open the book at circuit. So help each other. Those kind of problem, you see, you have to practice. You have your textbook and you have to practice a lot. Okay, because I make it like it's easy, but it's not that easy. It's just because I've been teaching the same stuff for the last 20 something years. But it's not that easy, okay? So here, you don't have to draw. They're just asking you to find the equivalent resistance. So you have a black box, okay? You want to replace the three of them in parallel by a single one. So they are in parallel, so you just use the magic recipe. Let me know what you get. 10? Yes, 60 to the minus 1 plus I'm slide 90. Why did I skip? Yes, you're right, 10. So 30 to the minus 1 plus 20 to the minus 1. Okay? Whatever you get, you flip. So 10 ohms. Do you agree? Yes. Okay, that's good. Find the current in the entire circuit. Entire circuit. So it means you replace your circuit by one big resistance equals to 10 ohms. I'm going to make a drawing, but actually you don't need drawing, but it's okay. I'm going to do 3 pipes. One pipe here, another pipe here. Okay, so this one is 60, this one is 30, the other one is 20. And I can replace that by a single one of 10 ohms. So everything happens like you replace this, it's a black box, by one single resistance equals to 10. And So that current here is the one that comes from the power supply. So what do you think I is? Huh? 9 amps, very good. You have 9 amps. Okay, so you have 9 amps here from the power supply. So the answer here is 9 amps. Okay? And then this current is going to split here. Some of it will go here, not much because it has a big resistance. Some of it will go here, I2, a little bit more, so twice as much. And some of it here will go here. So the ratio between this one and that one is 3, so you expect 3 more current here. Okay, so you can use Ohm's law. The voltage drop here is 90 volt. The voltage drop here is 90 volt as well. Don't wait for me, okay, do it. I is 9 amps. Okay, so 60 times I1 equals 90. So 90 volt equals 60 times I1. So I1 equals, very good, 1.5 amps. Then you don't even have to do the other computation because you see here it has half the resistance, so expect twice the current, right? But let's do it. Let's do it. 90 equals 30 times I2. So I2 equals 3 amps. So you divide the resistance by 2, the current will be multiplied by 2. And then I3, so we're going to do 90 equals 20 times I3. So I3 equals 1.5? 4.5, thank you, 4.5 amps. Okay, it has to be 3 times more than this one. Now, if you do I1 plus I2 plus I3, what do we get? 9 amps. Okay. So it's not, if you have the right methodology, it's not that hard. Any question? If you make the schematic like it's done in the book, because I use that methodology, but in the book they will say, okay, you have a power supply here, 90 volt, okay, you're gonna have one branch here with doesn't matter which one comes first, or maybe 60 here. I can put the 20 if I want, doesn't matter. And I have the 30 here, doesn't matter. So you have the current here flowing through the main branch, I, and that I is going to be 9 amps, right? So it's flowing here, flowing. And then it's going to split. So you're going to have this one, it's going to be your I1. This one, I call it I3. This one is going to be called I2. And then it's coming back here with 9 amps. Is that clear? So that's another schematic. Do I do number 2 or what? Okay, let's do number 2. Yeah, you have tutorial also in the Dropbox. Okay, so you have 3 15 ohms are connected in parallel and placed across a power supply of 30 volt. So first they want the equivalent resistance, right? So let's take your calculator, can help each other. So I'm going to do the magical recipe. Plus 3 of them, right? Five. Okay, I tell you a secret. If the resistance are the same, so we have 15 and 15 and 15. 15 divided by 3, how much is that? 5. Okay, so if you have the same resistance, all you have to do is to take 1 and to divide by the number of resistance. Okay, so 15 divided by 3 is 5. Okay? Okay, can you do this one? Yeah.
Could you do the same thing for each branch? Like divide by 3. Once you find out
Uh, oh yeah, you're right. Absolutely. If they have the same resistance, all you have to do to find I1 and I2 and I3 is to get the main current here that we're going to compute and you divide by 3. Yes. So 30 divided by, is that 6? Huh? I didn't make a mistake. 6I equals 6 amp. Right? Right? Okay, I want to make sure. So this is 6 amp. And someone said, okay, they are the same. So what do you expect in each one of them? 2. So imagine if they have the same resistance, that means your pipe has the same size. Same size. Same size of pipe means the same amount of water flowing. If you have a big resistance, that means the pipe is tighter. If you have a small resistance, you have a large pipe. So you expect more water. So I think, let's find out. I think that's going to be 2 amps. That's going to be 2 amps. And that's going to be 2 amps. Let's check. The voltage drop is 30 divided by 15. That's going to be 2 amps. Okay, so 2 here, 2 there, 2 there. Is that clear? Now, if you do the schematic, try to do the schematic on your notebook to make sure you know how to do it. So this is 6 volt. Do a schematic here. Okay, so if you do the schematic, that will be 1 here, and then another one here, and then another one here. So the current flow through the power supply here, I, and then you're gonna have, this is 6 amp, that's gonna be 2 amps, and then here also. So, oh, let me ask you something. Look at that. Can you look at this? You have 6 here. 2 is gone. How much is left here? 4. So then here, 2 goes. How much is left? 2. Isn't that fun? 2, and then 2, and then 2. So 2 and 2 is what? 4. And then you have 2. and 4 and 2 is 6. So you can imagine like little either water flowing or little marbles flowing, you see? 6 and then 2 goes, so 4 is left, 2 goes, so 2 is left.
But you're saying from bottom to the second line, it's 4 amps that's spinning through, correct?
Yes, so if I put a connecting wire this way,
Yeah.
okay, it depends how do you make your connection.
It depends on how you.
Yes, because if I connect straight, if I connect, that's a good point. It depends on the connection, because if I connect straight to the power supply, so if I do something like this, if I have a 6 volt, and all of them now are connecting here, okay, like this, I can do that as well. So in that case, that's going to be 2 and 2 and 2, and from here you're going to join 6. Okay, so here that means I took another connecting wire, right? But the idea is that at a connection here, intersection, the current add up. Does it make sense, right? It's like water flowing in pipes.
The current's adding up, but it's not changing actual current between.
No. So each resistance will get 2 amps. It's just the way it's the connecting wires. Okay, so 2, I don't know. Okay, let's do another one, but last one. Make sure you know. Okay, find the effective resistance. Can you do it? So 120 to the minus 1 plus 60 to the minus 1 plus 40 to the minus 1. So what do you get? 0.05. You flip, what do you get? 20 ohms. Do you all agree with that? Okay, so that's going to be 20 ohms. So everything happens like I have one power supply of 120 volt. I have in my black box a 20 ohm resistance. So what's going to be the current? 6, you're right, 6 amps. Okay, you see how it works? For each branch, so I can make another drawing. So 120 volt. Okay, I have my branches here. Boom, boom, boom. 120 ohms. And then I have 60 ohms. And then I have 40 ohms. And then I have 6 amp. Well, this one is easy. What's going to be the current here? 1. So this one will be twice because this is half, so 2. And how much is left? 3. Okay, is that clear? Now all across the branches, they are all happy because they get a power supply of 120 volt. Okay, so that's how it works. If you do the schematic, you're going to have 120 volt. That could be your AC, okay? Because even if you have AC, you can use Ohm's law. And you have 3 loads. Okay, maybe you have a hair dryer, you have your audio system, you have your laptop, and each one of them drain as much current as it needs according to its resistance. So everyone is happy. Any question? Okay, so here you have, they are comparing parallel in circuit and parallel in series. So here you have one pathway. Here you have two or more pathways. The voltage has to be shared. Okay, so here all of them have the same voltage. The current is the same all over in a circuit in series. Here it will add up to the main power current. Here for the equivalent resistance, it's adding up. Here you have to use that recipe. And if one bulb is broken, nothing works. Here it's fine. If one resistance doesn't work, or if you turn off your load, the other one can work. And here we go. Okay, so this is called Kirchhoff law for current. So each time you have an intersection, whatever comes in will have to come out. So if you have 7 amps coming in, and this one is 5 amps, so this one has to be 2 amps. Does that make sense, right? So if you have, I don't know, 10 gallons, and this is 6 gallons, so this one has to be 4 gallons. It's the same thing. Imagine water flowing in pipes. So this is called Kirchhoff's law for current. You also have Kirchhoff's law for voltage. Okay, so you have a voltage of 12 volt to begin with. You see, it's going to fall here by 10 volts. So how much is left? 2 volts. Okay, so that's what I did when I did in series, for example, here. You see that the power supply here is 30. This is 15. That's going to be also 15. It adds up to 30 volt. Now, you don't need to have the same, so maybe I'm going to increase the resistance here.
Does the law only apply to in series?
So, for the voltage, yes. So that will be for Kirchhoff law for voltage. Okay, the voltage, the sum of the voltage of the loads will be equals to the power supply voltage. And that will be for Kirchhoff law for current. So the current will add up. Okay, so it's a good question. I should show you that. Okay, so the voltage drop across 10 ohms, it's 4.29. Agree? And the voltage drop across this load, and they are in series, it's about 25.7. When you add them up, you get to 30 volt. So when loads are in series, you add up the voltage, and it will give you the voltage of the power supply. Yes? Now, if the loads are in parallel, okay, so if it's a parallel circuit, the voltage will be the same, but the current add up. So here you have 3, here you have 3, here you have 7.5. So when you add them up, you have 13.5. So this is called Kirchhoff law for voltage, and this is called Kirchhoff law for current. Is that clear? So in a parallel circuit, the current add up. In a circuit in a series, it's the voltage that will add up. Okay? So for example, here you have 10 volt and then 2 volt. It adds up to 12 volt. So it says Kirchhoff current law, Kirchhoff voltage law. Okay, so let's have some fun. Kind of fun. Let's do that in our head. Are you ready? You're all awake? You don't space out over there? Okay, so you have a 24 ohms, 24 ohms, 24 ohms. Are they in parallel or in series? Very good. They have the same number here, right? So what do you think the equivalent resistance will be? 8, very good. Everything happens like I have an 8 resistance, right? You can do the recipe if you want. So what's going to be the main current? What you will do? Well, exactly. So 12 equals 8 times I. How much is that? 1.5 amps. Do you all agree with that? Did you follow along? Okay, so the equivalent resistance is 8. So 12 divided by 8 is going to give you the main current, right? So it means here I'm going to have, what did we say? 1.5 amps. The flow, 1.5 amps. And then it's like a pipe system, plumbing. It's like a plumbing system. And they have the same size. All those pipes have the same size. So what you expect in each, 0.5 here, very good, 0.5 here, and 0.5 here. So at the end here, we're not going to make our life more miserable than it is. We're not going to worry here. Just there, you're gonna get 1.5, and it's coming back. Okay? Did you see what we did? Otherwise, you can always do 24 to the minus 1 plus 24 to the minus 1 plus 24 to the minus 1. Whatever we get, you do to the minus 1, and you have the equivalent resistance. So everything happens like you have a 12 volt with an equivalent resistance of 8 ohms. Okay? More fun. This one is more complicated, so I'm not going to do this one. Okay, let's do this one just to see if we know how to use the calculator. Okay, so you have 8, 24, 30, and 20. Can you find the equivalent resistance using that special recipe? 24 plus 30 plus 20. Are you with me? And I did a mistake. So don't wait for me. Answer the question. 8 plus 24 plus 30. I forgot the minus 1 plus 20. So do you get 4?
Yes.
Okay. Do you see that 4? Typical conceptual question for the test. The equivalent resistance that you get is always smaller than the smallest one. What is the smallest one here? 8. 4 will be smaller than 8 because in a parallel circuit, you are draining more current that you do in a circuit in series. So the equivalent resistance is always smaller than the smallest one. Okay? Number B, the current in the battery. So it's going to be 60, and then you divide by 4. 15 amps. Do you all agree? So the 15 amps, that will be what you drain from the power supply. Let's see, what else do they want? The current in the 8 ohms resistance. So it's going to be, what's the voltage across the 8 ohms? Across the 8 ohms, across all of them. 60, okay? In the parallel circuit, that's simple. They all have the same power supply across. So 60 divided by 8. So we get 7.5 amps. Okay? You see now? You're so good, you don't need to draw. Okay, the power in the 24 ohm resistance. So let's see what I am given to find the power. Do I know? I don't want to find the current. I'm lazy. But do I have the voltage? Yes. Do I have the resistance? Yes. Do we have an equation? Yes, which is very good, V square over R. Okay, so I use this one because that way I don't have to find the current. So I do 60 square, 60 square divided by 24. That's going to be 150. The power, okay, the power that will be turned into heat by the 20 ohm resistor will be 150 watt. Very good. So joules per second. It's Joule's effect. Okay, it's turning electrical energy into heat.
What was the answer?
150. Power. It's the answer. The power dissipated in a 24 ohm resistor is 150 watt. Any question? Right? Okay. How can we solve this circuit here? What do you see? You see, yes, parallel and series. Okay, so you see two branches. So do they have the same voltage? Yes, but then you have a series. So how are we going to solve this? You can also do it with in your head, but
Split.
we're going to split. Yes, exactly. We're going to split it. First, we're going to find the equivalent resistance for the parallel one. So now the goal is to find the equivalent resistance. Ah, move. No, move. Okay, let's do it this way. You take a walk, you start from here, okay? So you have 1.5 volt. Boom, 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 boom. Okay. Oh, what's happening here? See, you follow along. Huh? Yes.
Question. Just to make sure, so I know these two are parallel and that one's in series, but if we know that if it was in series, if we take out one of the bulbs, all the bulbs.
So yes, so if you yes, so if you break that, then the current cannot go back to base. So what's happening here at that point? Parallel. So I'm going to make a parallel. Boom, boom, boom. And then boom, boom, boom. So you follow along. You take a walk. Oh, two branches. Okay, no problem. I'm going to make two branches here. What's happening here? Series. So I'm going to have an 8 ohm. And then you go back to base. So how do you think we're going to solve that? First of all, I want to find the equivalent resistance. So first, I'm going to replace those two by 1, right? So I go step by step. So that's going to be what? Is that 18? They are in parallel. 4? 4. And then I just shift. I shift this one. You see? You shift this one. I just want to show you, and I will get back to that next week, but I want to show you how to do it so you can do the homework or do work on your MCAT, whatever. What do I have now? Yes, I have a series. So you can replace everything by 12. And what's going to be the current? It's going to be 1.5 divided by 12 amps. A little bit challenging. So try to do that for next time. I1, and then you have I2, and then it combines here. I3. Yes. Solve for what?
Like the voltage drop from out parallel to would you do the same thing just for like separated?
Separate them, and then you come back. So for example, can I say that the voltage drop here is 1.5 all the way? Yes, but here you have a smaller voltage drop, and here you have a smaller voltage drop. So did you find the current here? That's not I3, that's I. 0.125 amps. 0.125 amps. Okay, they don't ask you that. They just, oh yes, they ask you I1 and I2. So I will show you that it's 3:30, but make sure you go and study from the textbook, okay? So that will help for Tuesday. So this is called a complex circuit. So it's a little bit more challenging.